Thanks. No worries. No, thanks for the introduction. And actually, yeah, thanks also for giving me the opportunity to speak here. It's a great pleasure to be here. And I think you put me right on the spot after these two great speakers. I'm also looking forward, of course, to the next ones and then joining the panel. Of course, IQM is maybe not as prominent as what we have seen earlier. So I allowed myself to just start with a brief introduction to give everyone the chance to get to know it a little bit better. So we are a quantum computing company which was started in summer 2019. So we are still in our second year of operations, and we are building quantum computers based on superconducting technology. I think this is one of the reasons why we are here today, because we are discussing superconducting technology. What we are doing in particular, we are following a co-design approach for application-specific quantum computers, and I will try to use the main part of this talk to explain in a little bit more detail what we mean by this. We are now about 100 people strong in 2 locations currently. So our headquarters are in Finland, and in Helsinki. So you see on the bottom left actually a view from the office building where we are. And then we are also in Munich, and in both places we are still growing the team. As a startup, we are backed by venture capital, but then actually we're also involved in quite a lot of public R&D projects. And then we actually managed to get one case where we were able to sell a quantum computer to the Finnish State Research Center VTT. And you see the main summary on the top right, where actually we will deliver on premise for them the system in 3 stages, and you see the respective qubit counts. So we are at the moment working on the 5-qubit system for them, and then there will be 2 upgrades in 22 and 23. And this is one of the, let's say, bread and butter activities that we are doing in IQM, is kind of building the systems and the foundation of the technology to operate and scale them. And this kind of on-premise delivery of systems which are good for education and research, this is actually something that we are also planning to do more. And we are currently in a few discussions with other research institutions about delivering such kind of systems on-premise. However, since the main theme of today is the future of superconducting quantum computing, I don't want to spend so much time on talking about the systems that we built here, but more about, okay, where do we think the future is going to go? Maybe for those of you who are interested. So at the moment, just to give you a state where we currently are, as I said, we are currently working on the 5-qubit chip, and we reach, let's say, state-of-the-art coherence times for these superconducting transmon qubits that we are using here as well, and also on the gate fidelity side. We are getting, let's say, quite normal state-of-the-art results. So this is kind of where we currently are. But of course, for a startup in particular, it is also important to think about the future and also the near-term future, as we are depending also on future funding round. And this is why actually we think a lot about the future of superconducting quantum computing, and also what might happen before we reach the error correction. So we have heard a lot in the 2 previous calls about the error correction and how important this is. But of course, also there might be some benefits already beforehand. And this is something that we focus on a lot in this co-design approach that I will explain to you now in a little bit more detail. So let me start with a problem statement from our point of view, is that there is a gap between the requirements of algorithms for quantum computers and what the hardware can currently deliver. So I think this is the reason why many people put so much effort in the hardware development to make the systems larger and larger, and then the gate fidelities better and better. But I think still, until we reach this usefulness, still we have a significant gap to close. And the question is, okay, what is actually the best way to close this gap and to reach usefulness before we have fully error-corrected quantum computers? And the quantum advantage is a little bit like looking for the low-hanging fruits, of course. And you see here on the map on the right-hand side that I copied here a few of the fields where people discuss quantum computing and advantages in quantum computing. So our approach here is that we say, okay, if we want to be really hardware efficient, let's look at classical computing. And then usually what people do there is building application-specific systems. So in a sense, a very bare bone, no overhead approach to reduce the requirement to the qubit count and gate depth. And we do this in this co-design approach, which I will show you in the next slide, to then address certain applications on this map here. And I will pick later in my talk to chemistry and finance to say a little bit more about them. So what is the reasoning? Why do we think to kind of tap into the usefulness early on is going to be through this application-specific systems? So let's briefly review this, let's say, standard approach for quantum computing. And I think we have heard already a lot about how this works in the previous two talks. So we use superconducting qubits here, and then we arrange them in these square lattices, which we have seen nicely in John Martinez talks. And as he said already, is that the reason to design it in this way is to apply error correction, because this works nicely in this configuration. But then the error correction, as we all know, also creates a certain overhead in qubit count. So you need more physical on-the-chip qubits than you would have than logical qubits in the end. And this is why many estimations then they end up with these requirements of millions of qubits if you really want to run a fully error-corrected algorithm. And of course, you can then take this number of qubit and translate it directly into a number of years until you're there. Especially then if you're a startup company, this tells you that, okay, maybe you should do something in between before you reach the error correction. And this is one of the motivations here also for us to try to find also an alternative route. So the goal is to build something useful with maybe hundreds of qubits, because we think that this can be reached easier than the fully error-corrected scheme. And the path that we are following here is kind of extending a little bit the toolbox that we have. And I think one of the nice things in superconducting circuits is that the toolbox is so big, so you can really engineer these systems and play around with them. And then why not use this degree of freedom? And these are the considerations that we do here. So on these three levels that you see here, so for instead of only using qubits, square lattices, and then single and 2 qubit gates, that extend them. And this means that on the element side, so what we put on the chips, instead of maybe only using qubits, we can also consider higher level energy levels of these circuits. And there have been a few recent papers actually also published or on the archive about this, on how to build quantum computers. And then we could also actually use the resonators that we usually only use for readout. We could also use them to provide bosonic degrees of freedom, and in this way implement a more direct simulation loop tool, for example, for bosonic degrees of freedom. And then on the chip itself, we have, of course, the degree of freedom to not use this square lattice approach, but we could try to arrange the qubits in a way that they fit better to a certain algorithm. So for example, instead of a square lattice, use an hexagonal or a triangular lattice, whatever we think is good for a given algorithm. And then finally, on the gate level, also here extending from single and 2 qubit gates to what we call analog blocks. So this means kind of turn on the resource interaction between several, so more than 2 qubits on the same chip. So these are the kind of elements that we are exploring and that we are using to build very hardware efficient systems. And how we kind of approach this is that we, on a very high level, we separate the problem into these three stages, or let's say it's a very simplified stack of a quantum computer. You have the applications on top, and then the algorithms in the middle, and the processors on the bottom. So here you see a superconducting flip chip that comes out of the foundry that we are using here in Finland, for example. And the idea is between these stages always to really optimize the mapping so that we don't lose anything on the hardware overhead side. And this optimizing the mapping we do by applying these tools that we have seen in the previous slides. So for example, apply the digital analog algorithms, or then adapt the chip architecture to the problem to reduce the hardware requirements in the upper level, and then on the lower level, we can use additional on-chip building blocks like these qubits, or for example, individualized chip design where, for example, we adapt the coupling between different qubits depending on what serves best certain algorithms. So this is kind of the high level idea that we are exploring here to reduce the hardware overhead. And now coming from this general concept, let's have a look at two examples. So the main question, of course, is which are the low-hanging fruits if you are here on this landscape? And of course, there are various opinions on this. And what we are doing in IQM is talking to several other companies, either from industry or then also from the quantum software side, to find out actually what are the good problems that we should tackle. And at the moment, two of them we are looking into are in chemistry, one and then one in finance, where we are really trying to find out, is there a way to optimize the chip design so that we can reduce the hardware requirement? And I will just try to give you the high level idea for those two in the following slides. So let's start with the chemistry side. And I think this is well known that a quantum computer can be used to describe certain properties of molecules, and then there might be potential speed up, and we can either look in equilibrium properties, but then also dynamical properties of these materials. And the usefulness of quantum computers comes because of the complexity and the way it grows, especially if the system side grows. In particular, if we turn on strong interactions and correlations in the systems. And this is when then often the commonly used tools like the DFT or so is breaking down because of the strong correlations. And one example for this is this FEMO cofactor, which is kind of en vogue field of study because it is a major part in this nitrogen fixation process. So this is one of the fields I think that's well known to the community. And usually the approach is that we qubitize the system. So we try to use directly the qubit degrees of freedom. And then we use some well-known algorithms like the phase estimation algorithm or the VQE algorithm. And the challenge here is that usually then the number of qubit grows immediately with the system size. And this, in a sense, postpone this quantum advantage or the time when we reach it. So we are thinking here about a slightly different approach where we use a DMFT, so dynamical mean field theory, and apply it to impurity models. And the idea now behind this co-design is that we really try to implement this kind of impurity system in a continuum of modes directly in the chip, and try to see if we can gain advantage here for certain applications, especially when the correlations become very strong, and then it goes into these strongly correlated systems that are interested also for scientific reasons at the moment mainly. So these are the considerations that we have, and we have some good preliminary results, which we are still challenging with a scientific community before going out with publishing them. But the idea is really try to implement this problem in such a chip architecture, and then kind of come up with a more general approach so that you don't always need to really update the chip architecture, but really find a way to also then map several different problems into the same chip. So this is the idea for chemistry. And then we have one in finance where I will hope in the second slide also to show you why the hardware is so important to take into account. So in the field of finance here, there's a cite here a paper from derivative pricing from a group in Bilbao, where for a very specific problem, they have estimated here the hardware requirements, which actually sounds quite low, and which is nice. And the reason is that they used a slightly different approach by directly implementing a differential equation solver for the black skulls to find the properties. And the advantage is that you reduce the hardware requirements. The disadvantage is that you really restrict yourselves in the boundary conditions and so on. So the usefulness might not be so strong anymore because you can also do it with classical computers. But our idea now kind of is that, okay, use this as a starting point and then try to work our way forward in optimizing the chip architecture and bringing in more and more complexity into the problem so that there will be a real world use case with a designated chip for this. And just to show you how we bring this to the hardware side, I have now copied from this paper the algorithm that you see here and the different blocks that are being executed. And what we do in IQM is thinking about, okay, how can we improve on all of these individual blocks from a hardware perspective and make the operations better. So for example, on the initialization of the qubits, we are investigating on-chip reset tools, which are based on SINs, the superconducting insulator normal metal junctions, which in a sense provide a very cold bath, which can be coupled or decoupled from the qubits, and in this way reset the qubit to a very low temperature state within a few tenths of nanoseconds. On the gate side, we are actually also investigating different qubit types that go beyond the standard transmon, and we have some promising preliminary results, which we are still checking now experimentally. And we are also looking into applying continuous gates. For example, I quoted here some work from the Walraff group in ETH, where they show that you can reduce the gate depth, for example, by using these continuous gates. I mentioned already this digital analog scheme, which can be used to replace cascaded 2-qubit gates. So this goes back to some research done by the Bilbao research group, where I cited this paper from. And then finally, at the end of the algorithm, when you do the measurement and post-selection, we have been developing some alternative approach to the standard dispersive readout scheme in superconducting qubits, which is able to speed up the readout process. And also we are looking a little bit into the future, and there's some work on bolometer readout, so direct readout of the cryogenic microwave. So this is a paper treating with graphene-based bolometers to detect the microwave signals. So this, in a sense, shows you a little bit on how really the hardware can be directly connected to the algorithms and provide the advantage. And of course, all of this is not only to stay then within these very narrow application-specific approaches, but we also see this then as an enabler and to provide synergies for error correction, because in a sense, these basic operations that you saw on the previous slide, like initialization or reset, then the gates, and then the readout, these are also the basic blocks that you need in the error correction scheme. So the better you do those and the faster you can do those already in these NISQ applications, also the better you are then later on when you reach the error correction schemes. So this is it from my side. I just also, as a maybe inspiration for the panel, just a few personal views on the future of superconducting quantum computing. So my view is that quantum advantage will first emerge gradually, application by application, until we see this broad quantum advantage from error-corrected systems. I think that in the very beginning, we will see several technology platforms coexisting, and they all have their reason to be there, because I think that some technology platforms are better for certain algorithms and some are better for others. I think that really we need to streamline the processors for certain algorithms if we want to reach the quantum advantage in the fastest way possible. And this is also the reason why I think that these hardware agnostic software platforms in the beginning will not utilize the best performance of the systems. And then finally, I think that quantum computers, in a sense, should be highly integrated into high-performance computing centers. And this is actually something that we do actively. For example, in Munich, we are working with a local supercomputing center, LRZ, there to build a system into their infrastructure and see how they can work together. All right, so this is all from my side. Thank you for your attention, and I'm also happy to take any questions.
Thank you very much, Jan. So let's see if there are any questions. So yeah, I was wondering which kind of different architectures have you been in practice, testing. You mentioned the DMFT kind of experiment, but do you think that certain architecture could give you an advantage, in applying DMFT over, classical calculations current
Yeah,
that are available?
this is exactly the idea here. And the question is on the chip, how can you, it's more than like, let's say, going into the direction of simulation, how can you implement this impurity in the bath, and how can you create these on-chip elements so that the physical chip more or less directly implements the physical model that you have on the paper. In this way, you kind of directly implement the problem onto your hardware.
People are interested to know whether you have tools like this DFT tools that you mentioned, which are available. They're publicly available, or are you going to make them publicly available?
Tools.
Yeah, you mentioned you're developing software tools.
Okay, yeah, so we are, in a sense, since we are building the computers, we are focusing on the hardware. And I think soon, for example, we will open source some of the software tools that we use for the design circuits and these things. But then at the higher level, to access the systems, we will integrate into the existing software frameworks that are out there. And we will not reinvent a new high-level programming framework.
I see. Okay, another person asks here, how do you check the quality of your chips?
Yeah, that's a good question. I think this is something that, in a sense, you have to get a change in your mindset when you leave the academic university environment, where basically you try fabricating chips until one works. So what we do a lot is kind of just routine fabrication of chips with very well-defined test structures. So let's say single qubit, 2-qubit gates. And then we have designated cryostats for those chips, where we just cycle them on a regular basis, and then in an automated way just measure T1, T2, and these things and put them into our database. So this is kind of bringing the academic mindset into the system engineering mindset that I think the whole community somehow has to undergo currently a little bit.
Okay, so yeah, thank you very much.